In this second example, I would like to highlight the symmetrical case. For example, in this case, a continuous aluminium frame structure built to support a uniformly distributed load of 10 kN per meter in the direction as shown. The structure is fixed at points A and E, while points B and D are being supported with roller pin support. Young modulus for aluminium is 70 gigapascal and its Poisson ratio is 0.3. So in this case, we just need to determine the unknown displacement. All the parameters, for example, cross-sectional area and area moment of inertia is given in this table. So for a symmetric case, in order to determine either the structure is symmetrical or not, we have to check the condition. Normally, there are three conditions that we must check. The first one, the applied load must be symmetrical. So we have to check in this case, we can see that on the left side, BC and CD are having a symmetrical load, meaning that having the same load. And then the geometry must be symmetrical, meaning that the length, the cross-sectional area, everything must be equal on the left and the right side. And the last one, the boundary condition or support must be symmetrical. So if we check in this case, point A and point E having the same boundary condition, point B and point D having the same boundary condition, which is pin roller support, and point C is in the middle. The load is symmetrical, the length is symmetrical, so we can consider in this case, this structure or this problem is a symmetrical case problem. So in order to solve this problem, we can cut the structure into two to simplify, so that we just need to solve this problem by using two elements. So in this case, of course, we have to cut at point C. So at point C, we cut. So please take note that at the point or the section that we cut, the boundary condition have to change to a fixed roller support. Wherever the problem is, if you are trying to solve the truss problem or the beam problem, if we are dealing with symmetrical case, and when we want to cut the structure to simplify our calculation, the section that we being cut must change the boundary condition to a fixed roller support. Remember, fixed roller support. Okay, fixed roller support again. So after we cut, then only we can determine the degree of freedom at each node. In this case, as node A is a fixed joint, therefore all the degree of freedom is 0. UA, VA and theta A is equal to 0. While at point B is pin roller support. Okay, so pin roller support meaning that UB is equal to 0. It cannot move in X direction, but it can move in Y direction, and S is been pinned. Okay, so pin joint, so it will have rotations. Okay, remember, so pin roller support will still have the theta B because it's a pin joint. While at point C is a fixed roller support. So you must see the difference between pin roller support and fixed roller support. When we talk about fixed roller support, so the keyword there is fixed. So when fixed, theta is always 0. That's why for point C, theta C is equal to 0. UC, of course, will equal to 0. And only VC is unknown. So in this case, there are three unknown degree of freedom, which is VB, theta B, and VC. Please remember, pin roller support and fixed roller support is not the same. Okay, for pin roller support, theta still exists, meaning that it still can have rotations. But when you talk about the for fixed roller support, then it cannot rotate. So the rotation will equal to 0. Once we have determined the unknown degree of freedom, the next step is to obtain the stiffness metric for each element. So we start for the element 1 between node A and node B. So in this case, we will connect the element from node A to node B. So by referring to our K frames global matrix, so we have to arrange the columns according to element connectivity. As mentioned, as we connect the element from A to B, therefore the first column will start with UA, followed by VA theta A for node A. And then it's followed by UB VB theta B for the second node, which is node B. And then, as similarly to the previous example, in this case, we also just want to solve for the displacement. We have no interest on the reaction force and so on. Therefore, we can eliminate those row and column from the beginning. So for that, we have to refer to our boundary conditions, which is for element 1, we know that UA, VA, theta A, and UB is equal to 0. Thus, we can eliminate those row and columns. For example, row and column UA, row and column VA, row and column for theta A, and the last one, row and column for UB. So, only this parameter that we have to solve in order to obtain the stiffness metric for element 1, only 4 parameter. Similarly, for element 2, is between node B and C. So we connect the element from node B to node C. So our arrangement of the matrix in our global K matrix will start from UB, VB, theta B, followed by the second nodes UC, VC, and theta C. Remember, it's always start from X, Y, and Z. So UB, VB, theta B, UC, VC, and theta C. And we can apply the boundary conditions so that we can eliminate those unwanted row and columns. So for element 2, UB, UC, and theta C is equal to 0. So we can eliminate those row and columns so that we just need to identify those related parameters that we have to solve. For example, in this case, we have these 9 parameters that we have to solve. Next, similarly, in the previous example, so we need to identify those important parameters into the tables so that we can solve for the A, for the I, for the K, and the B, as well as the theta. Okay, the theta is depend how you connect the element. For example, in this case, we say that for element 1 is A to B, so our theta is equal to 90 degree. For element 2, we connect it from B to C, and our theta is 11.31. And the rest, we just need to apply C is equal to cos theta, S equal to sin theta, and so on. So for the first element, we just need to refer back to our K matrix that we had identified just now. So we just need to solve these 4 parameters so we can obtain our K1. And we do the same for the K2. So we just need to refer back to our K matrix and those identified parameters that we need to solve. So by replacing the value from the table, then we can solve for K2. Next, we just need to obtain the global stiffness matrix. So in this case, by combining the matrix K1 and K2 according to its position, so we can obtain our K global matrix. For example, the first term here, VB and VB, is 2800, and from second element we also have VB and VB, which is 63.4. So we just need to add to the first term here. That's why we obtain 2863.4. And we do the same for the rest of the column and row in this reduced global stiffness matrix. The next step is to obtain the equivalent values of the relevant applied nodal loads. As in this case, the frame also has been loaded with uniform distributed loads between nodes B and C. However, the distributed loads is acting on the local direction. Therefore, by using these equations, so we can solve these distributed loads to obtain the equivalent forces and moments in the local direction in the first place. Okay, therefore by using this equation, then we can solve the force and moments at node B and node C, which is in the local direction. For example, FB here, so we have FB into these directions, in the local directions, as well as moment. And at point C, we also have FC and moment at point C. They have no force in local X direction, as the local direction for X is always equal to 0 from the equations. That's why we only have local force and moment in local Y and Z direction for the moments. Next, we have to resolve these forces into global direction, meaning that we have to resolve to Y direction, as well as we need to resolve this into X directions. In order to convert the local forces into global forces, first we need to determine the value of beta, which we already determined in the previous step in the table, remember. So the beta is equal to 11.31. However, as we want to convert from local to global, meaning that in this case, from local to global, it will move into clockwise direction. Here we can see that it moved from local to global in the clockwise direction. So whenever the angle, when it moves clockwise, we always consider the theta is negative. Okay, so we always consider that the angle is positive if we move counterclockwise. That's why in this case, the beta here, I put negative, as it moved from local to global, meaning that it's moving clockwise. So in this case, we just need to resolve by knowing this beta. So we know that to obtain the FBY, this FB just need to multiply with cos beta. It's okay if we don't know either the theta beta is negative or positive, as long you know the directions. Okay, as long you know the directions, then we can determine either the value will be positive or negative. And the most important is to know the angle. Okay, then how to convert? Okay, just need to multiply by sine or cos by using the trigonometry that you have learned before. And then you just need to look on the directions, then we can determine either it's positive or negative. If you want to know negative or positive automatically, then you have to decide. For example, from local to global, it moves clockwise. So when clockwise, the angle must be negative. In this case, if you apply in this way, then you will obtain the value automatically positive or negative. Okay, but it doesn't matter, as I mentioned. You also can determine negative or positive by looking at the direction of the force when you resolve into X and Y. For example, in this case, of course, we know that when you resolve into FCY, as it moving downward, so FCY will be negative. And when you resolve this FC into FCX, we can see that the direction of FCX will be to the right, which is positive. Okay, so the most important is to know the theta here. As I mentioned, the direction positive, negative, you can look on this direction here. Once we have solved the equivalent global forces and moments, then only we can set up our system linear equation as shown in this slide. For the first unknown, which is VB, which is related to the vertical force at node B. For that reason, we have to refer to the node B vertical force, which is FYB. And the value here is negative 50,010. So that's why we replace this value into this equations. Then the second term is theta B, which is related to moment at point B. So what we have to do, just need to refer to the moment at node B, which is MZB, equivalent to negative 86,700, and we replace into these equations. And the last term is VC, which is related to vertical forces at node C, which is FYC, given by this value, and we just need to replace this value into these equations. Then only we can solve the unknown displacement by using the calculator, and the result as shown in this slide.